Hey folks, I hope you're doing well. This is a continuation of the earlier video about linear functions. And we are going to pick up today, jumping right in, start talking about horizontal and vertical lines. So in the last video, we talked about how a linear function in general has the form f of x equals mx plus b. We understand that m is the slope, b is the y-intercept. We talked about graphing linear functions, finding their x-intercepts, and some other stuff. A couple of special cases. So one thing about linear functions, of course, is the graph of a linear function is a line, a straight line. And there are two sort of special cases of lines that are worth considering: horizontal and vertical lines. So a vertical line, you can see three vertical lines drawn on the graph here: the blue, the purple, and the sort of olive greenish color over here. Vertical lines have equations of this form, and these are not functions. They're not functions because they fail a vertical line test. If you put a vertical line down right on top of this blue line, it hits the line everywhere, whereas we need it to hit the curve only once if the curve is going to be the graph of a function. So equations, you can have all sorts of equations in x and y that aren't necessarily functional equations, and their graphs can have all sorts of different shapes. This is, again, a very special case. The equation x equals 3 graphs as a vertical line, and notice it goes through the point x equals 3 on the x-axis. X equals 6, vertical line through the point x equals 6, x equals -2, vertical line through the point x equals -2, and so forth. So this is kind of a special, exceptional case that's worth incorporating into our study of lines. Horizontal lines actually fit into our framework, but they're worth singling out. A horizontal line has a slope of 0. This makes sense. We think of the slope as the sort of steepness of a line, and a horizontal line is perfectly flat. It doesn't have any steepness. And if the slope is 0, then y equals mx plus b becomes just y equals b. The mx part goes away. So you can see here we have three horizontal lines, right? Y equals 1 is the orange one. It goes through the y value 1. Y equals 4 is the green one up here through the y value 4. Y equals -3 is the blue one at the bottom, goes through the y value -3. So again, couple of special cases worth keeping in mind. You've heard these words, parallel and perpendicular, I'm sure before. I'm sure you know what they mean, right? Parallel lines are lines that don't intersect, that just sort of run in exactly the same direction, right? So rails on a train track is a common visualization of parallel lines. And it's not too surprising, I don't think, that parallel lines have to have the same slope, right? Two lines need to have exactly the same steepness. If they are sort of slanted differently, then they're going to run into each other at some point. So this is a nice, easy algebraic characterization of parallel lines. And in particular, we can tell if lines are parallel. We don't have to graph them and try to eyeball whether they meet or not. We can just figure out their slopes, and if they're the same, then they're parallel, and if they're not, then they're not parallel. So here, slope of this line is 4, right? We know that the m is the slope value. Slope of this line is 4. So these two lines are parallel. Very easy to tell just by looking at the slopes of the lines. Perpendicular is slightly more complicated. Geometrically, we know that perpendicular lines meet in sort of a perfect plus sign, right? They form 4 90-degree angles. In terms of slope, it turns out that perpendicular lines have slopes that are what are called negative reciprocals, and we'll look at an example in a minute. So this means if two lines are perpendicular, when you multiply their slopes, you get -1. This is a little difficult to justify. There is sort of geometric argument you can make that shows this, but it would take us about 20 minutes and it's not worth it. So we'll just accept that for perpendicular lines, their slopes are negative reciprocals. And I think here is an example, right? So here's the slope -2. The negative reciprocal of that, I have to do two things: take its reciprocal and negate it. So the reciprocal of -2 is -1/2. And when I negate it, I get +1/2. So this line has slope +1/2. So those two lines are perpendicular. And I can check this just by multiplying the slopes of the two lines. -2 times +1/2. If I get -1, they're perpendicular. All right, so we have pretty straightforward ways we can tell when lines are parallel or perpendicular just by simple calculations involving the slopes of the lines. We don't have to graph and guess. In fact, graphing and guessing is a bad idea because it can be difficult to tell from a graph whether lines are parallel or perpendicular, but we can tell easily from their slopes. Okay, so one last notion in in this section about graphing of lines, and we'll talk about some application examples. How do you find points where lines intersect? So we know that parallel lines don't intersect. That's what it means to be parallel. But there's lots of lines that aren't parallel, and so they are going to run into each other at some point. And here are two examples, right? This is a linear function, h of x. The slope is -1, right? Because the slope is the number multiplying the x. And the y-intercept is here 6. Another linear function, slope is 2, y-intercept is 8. How do we find the point of intersection of these two lines? Well, again, you can graph and guess, but that's imprecise. You're not going to exactly find the point of intersection. You'll just find it approximately. What we'll do instead is rely on the fact that the point of intersection is on both graphs, which means that both functions have to have the same output value at that input value, right? Because it's points on both graphs. So what I can do is I can just set the two output formulas equal to each other. 6 minus x equals 2x plus 8. And I get an equation that's not too bad to solve. So let's go ahead and solve that equation. So let's see, what did I do? I added x to both sides rather. So the x moves over from left to right. And then I'll subtract 8 from both sides. And then I'll divide 3 by both sides. And so I get x equals -2/3. And what we have found is we have now found the x coordinate of the point of intersection. So we're kind of halfway there, right? Point of intersection has, at any point, has 2 coordinates. This is the x coordinate. How do I find the y coordinate? Well, the y coordinate is going to be the same on either function. So all I have to do is take this x coordinate and plug it into either one of these functions to get the y coordinate. So pick whichever one looks easier. I guess I thought h was easy. So here I'm just pointing out that it doesn't matter, right? You can plug into either function and you'll get the same y value. And you can check this actually as an exercise. So I plug into h here. So that's this function, 6 minus x. So h of -2/3 is 6 minus -2/3. That comes out to 20/3 when I do the math. And I think just for illustration here, no, I didn't, but you can check that if you do this calculation, you should also get 20/3. So it doesn't matter which one you pick. So this is the output value or y value at the point of intersection. So here's our point of intersection. The x coordinate we found was -2/3, the y coordinate 20/3. Some of you may know that there are other methods for finding points of intersection, but one is good enough for this. This method will always work, so we can always find the point of intersection. And here's a quick picture of what's going on. Here are the graphs of my 2 lines, right? The blue line clearly has a negative slope. It runs downhill, so it makes sense that it's the 6 minus x line. And the orange line has a positive slope, right? That's the y equals 2x plus 8 line. You can see the y-intercepts, right? The orange line has a y-intercept of 8, where the arrow is now. The blue line has a y-intercept of 6, right? And here, this purple point, of course, is the point where they cross. And these coordinates look about right? -2/3 and 20/3 is what, almost 7, right? And that's about right. Okay, let's look at just a couple exercises real quick, and then we'll talk about applications. Again, these are coming from the notes and exercises document. I'm in section 2.2. Okay, graphing, again, it's not a huge deal to be able to graph by hand, but it is useful to know quickly what a graph looks like and not always have to run to a machine to draw the graph. So this line right here, this is a linear function. When I see this, I'm thinking immediately slope -3, y-intercept 4. So on a graph, right, the y-intercept is probably the first thing I would do. And then with a slope of -3, I can just go over 1 down 3, over 1 down 3, and draw a line like this is one way to do it. Alternatively, I could just generate a second point on the line, right? I know the point 0, -4 is on the line. I could plug in another x value and generate a new y value. Here I have slope 2, y-intercept 5. Right, so I might start with a y-intercept of 5. I can see that when I plug in, let's say t equals 2, I'm going to get an output of 9. So I have 2 points on the line already, 0, 5, and 2, 9, and that would be enough to generate the graph. Here's 0, 5, and here's 2, 9 over here. And I know the graph is a line, so I can just connect the dots for my line. And finally, x equals 4 is a special case. That's a vertical line through the x value 4. So here it is over here on the right, this sort of dark line. Okay, 1 or 2 more exercises. So here we're trying to find a formula for the linear function with these different criteria. In the first one, we're given the slope and the x-intercept. Be careful, that's the x-intercept, not the y-intercept. So the answer here is not y equals negative 3x plus 15. Rather, what I have to do is use the fact, that this line has slope negative 3 and passes through the point 15 comma 0, right? That's what x-intercept 15 means, that the x-intercept is on the x-axis, so we'll have a y-coordinate of 0. And you'll recall, if we know the slope and we know a point, we can use point slope form to go ahead and write down the equation, right? So y minus y1 equals, there's my m, x minus x1. Then if you do a little bit of algebra, you can rearrange that and it looks like this. Okay, line passes through a given point and is parallel to this line. You'll notice that this equation, 2x plus 3y equals 18, is not in y equals mx plus b form, but that's no big deal. You can take an equation and rewrite it in all kinds of different ways by adding things to both sides and multiplying things by both sides and so forth. So if your equation's not in y equals mx plus b form, it's often convenient to make it look that way. Sometimes this isn't a big deal, but here I'm going to go ahead and do this, right? So I start here, I subtract 2x from both sides, and then I divide both sides by 3. Be careful when you divide both sides of the blue highlighted equation by 3. I have to divide both terms by 3, right? So 18 divided by 3 gives me the 6, and 2 divided by 3, of course, is 2/3. Okay, so now it's in y equals mx plus b form. Why did I do that? Oh, the reason I did that is the line I want is parallel to this blue shaded line, which means it has the same slope. And now I can see that that slope is negative 2/3. So I want a line with slope negative 2/3 passing through the point 512. I believe that's the next thing I say here. Indeed, slope negative 2/3 passing through 512. And again, if you know the slope and you know a point, the easiest thing to do is just use point slope form and write down the equation of the line. And so that's going to look like this. Y minus y1 equals slope times x minus x1. Okay, and you could, again, do some algebra to clean that up if you wanted to, but we have the equation that we want. And finally, a horizontal line passing through this point. Horizontal lines have the form y equals number, right? Their slope is 0, and the y value here is negative 2. So this must be y equals negative 2. I think that's our last solution here. Indeed. Okay, let's see. And finally, finding a point of intersection here. So this is similar to the example we did a moment ago. I'm going to start by equating the two outputs, because where the lines intersect, they have to have the same output value. And so here we go, right? We set the two outputs equal to each other. Then we just have to do a little bit of algebra. Right, so I'll add 2x to both sides. That gets me to here. Then I subtract 3 from both sides. That gets me to here. Divide both sides by 6, and that gets me to the solution, which is x equals 5/3. So that is the x coordinate of the intersection point. To find the y coordinate, plug that into either one of the functions, right? Either side of that equation. I use the left, so 4 times 5/3 plus 3 comes out to be 29/3. And so there's my point of intersection. 5/3 comma 29/3. And again, I think I have a picture down here so we can get a look at this. The graph isn't necessary. Once you reach this point, you solve the problem. This is just sort of a little extra information, right? So here are my two lines, and there's the point where they meet, 5/3 comma 29/3. Okay, let's talk a little bit about modeling with linear functions. What's going on here in this section is we'll have these scenarios like this one, for example, where we have two variables and the variables have a linear relationship, and we'll use that relationship to answer questions about the scenario. Okay, so Sue saved up $3,500 for her summer trip, and she anticipates spending $400 a week while there. So this doesn't really ask questions yet. The questions will come below. It just sort of lays out a scenario. First question, what are the two relevant variables? and which do we think is the input and which do we think is the output? Because again, in this class, our models will always be functional relationships. So there's always an input variable and an output variable. Well, I think that one variable is the amount of time that she spends there, right? Her spending clearly depends on how much time she's there. So I'll let W be the number of weeks she spends on vacation. And the other variable, of course, is how much she spends. Or actually, I'm going to use the amount she has left. And which variable you use kind of depends on which question you want to answer. So just in answer to this question, I think either amount left or amount she spends is a reasonable answer to that question. But I'm going to use amount that she has left. Notice that the units for W are number of weeks and the units for L are dollars. Okay, so what is the relationship between L and W? L is my output variable, W is my input variable. Well, if you can determine this right off the bat, that's great. If you're a little bit stuck, then pick some easy values for the input variable and figure out what the output is, and do that for a couple different values and see if you can see the pattern, right? So when W equals 1, she spent 1 week in San Diego, which means she spent $400, and she started with 3,500, so she's down to 3,100, right? So when W equals 1, L is 3,100. When W is 2, she's been in San Diego for 2 weeks. She spent $800, so she has 3,500 minus 2 times 400. And as you're figuring out L, it's useful to sort of slow yourself down and ask you exactly what calculation you're doing in order to come up with the result. And you can probably already see the pattern here if you didn't see it at the outset. L is going to be 3,500. And then the W value is going right there, right? It multiplies the 400. So the formula we want is 3,500 minus 400W. This is certainly a linear function. I can see that the y-intercept is 3,500 and the slope is negative 400. Note, and that's what I just said, and notice that these numbers both have interpretations in the problem, right? 3,500 is her starting amount of money, and 400 is the amount she spends each week. Okay, what is the horizontal intercept of this function? So horizontal intercept is sort of a silly way of saying x-intercept, right? It's where it intercepts the horizontal axis. Now, when you're looking at a linear function, the y-intercept's easy to find. It's staring right at you. It's the 3,500. How do you find the x-intercept? Well, remember the x-intercept of a function occurs when the output is 0, right? The y value has to be 0 in order to be on the x-axis. So all I do is set the output equal to 0. This is generally true for functions, right? The y-intercept is the function value at 0. The x-intercept I get by setting the output equal to 0. All right, so I solve the equation, add 400W to both sides, divide both sides by 400, and I come out with that number, 8.75. This has an interpretation in the problem as well, right? Because this is a W value, right? W is 8.75. So it's a number of weeks because that's what the input variable is measured in. And it's the number of weeks until her amount of money left is 0. That is, this is how much time she has until she's out of money, 8.75 weeks. All right, common questions when you have a model like this with an input variable and output variable. There are two sort of flavors of common question. There are more than just these two, but two major ones is here's an input value, what's the corresponding output? And then second category, here's an output value, what's the corresponding input? So this is the first of those. How much money will she have left after 5 weeks? Is saying if the input value is 5, right? The input is the number of weeks, what will the output value be, right? How much money will she have left? So another way to phrase this in terms of our variables is if W is 5, what is L? And this is pretty straightforward for linear functions, right? If you know the value of one of the variables, you can just plug in and figure out the other one. So I think we do that here. Yep. Right. So I plug in a W equals 5 into the formula, do the calculation, and I come up with $1,500. And this next question is sort of the reverse direction, right? It says if she wants to leave when she's down to 1,000, how long can she stay? So here I'm being given an L value, right? That's an amount of money, and I'm being asked for a W value, a length of stay. So in terms of our variables, this question is, when L is 1,000, what is W? Again, when you have a linear function relating the variables, if you have one value, finding the other isn't too bad. So I will just substitute a 1,000 into this equation for L, excuse me. And I reverse sides of the equation, which is fine, but just to make this look a little bit more like the above, let's do it that way. And then we just do some algebra here to figure out W. Right, so you rearrange, subtract 1,000 from each side, divide both sides by -400, and I come out with W equals 6.25 weeks. Okay, what is the domain of this function? Well, if we're just given a formula like this, and when let's say we had no meaning for L and W, right? Some of the exercise just wrote down, consider the linear function L equals 3,500 minus 400W. Well, the domain of a linear function is all real numbers, but this is not a context-free situation. These variables have meaning. W is a number of weeks, L is an amount that she has left. So there are some values that don't make any sense for the variables. For example, and what we're asking for is the domain, right? So that's the set of allowable input values. So we're focused on what W values make sense in this problem. Well, certainly negative numbers don't make sense. She can't spend a negative number of weeks in San Diego. So W has to be greater than or equal to 0. Hopefully that's the first thing that I say. And the other thing is that if we go past this 8.75, she's going to have a negative amount of money, right? So that doesn't make a lot of sense either. I suppose that's debatable. It's possible she could be in debt, but I'm going to consider this to be the domain, the interval from 0 to 8.75. And here's a quick picture, right? So all I've done here is graph this linear function, which hopefully is something that would be pretty routine for you now. Here's the y-intercept, 3,500. The slope is clearly negative, right? It's a downhill line. And notice the horizontal axis, we have the input, number of weeks. Vertical axis, we have the number of dollars left. All right, let me do one more. Yeah, I think one more is what we'll have time for in this video, and then I will point you to a number of other examples you can work, excuse me, on your own. Okay, so here's the scenario, right? Town's population is growing linearly, and we have a couple of data points, right? In 2004, the population was 6,200. 2009, it had grown to 8,100. All right, again, we're going to start by identifying the input and the output variables, and then coming up with a relationship between them. Well, the variables here, I think, are time and population. So let's identify those as such, right? I'll let T be time. Now, when you define a variable, don't just write T equals time. That doesn't make a lot of sense. What does it mean for a variable to be time? A variable is a number, right? So if your variable is time, it counts the time from some starting point in some unit. And it's good practice to specify both. So I'm going to let T be the number of years after 2004, right? If I just tell you time equals 5, it's not clear what that means. But if you know my time counts hours since noon, or years since 2004, or weeks since January 1st, or whatever, now when I say T equals 5, you know exactly what I'm talking about. And I'll let P be the population of the town. So time is the input here, population is the output. What's the relationship between P and T? Again, if you are stuck on this, I mean, we know that there's a linear relationship because the problem says that there's a linear, that the town's growing linearly. So right away, we know, let's do a little preliminary here. We know that P is equal to MT plus B, right? As soon as we read growing linearly and as soon as we identify the variables, we can write this down right away. So the only question really is what's M and what's B? Well, the information we're given is that these 2 points are on the graph, those 2 points, right? because 2004 is time 0. That's 0 years after 2004. And when the time is 0, the population is 6,200. 2009 is time 5, and the population then is, 8,100. And that's where I get those 2 points. So now this is becoming like an exercise we've done before. I will calculate my slope. Already set that, don't need that one. I will calculate my slope, right, by doing just the slope across these 2 points, which we talked about in a previous video. So I do change in y over change in t, in this, or change in p over change in t in this case. And that comes out to be 380 when you do the math. And I have the y-intercept actually right here. One of my points, just by good luck, happens to be the y-intercept, and I can see that because the input value there is 0. So I know the slope, I know the y-intercept, I can write down the formula, 380t plus 6,200. All right, what does this model predict the population of the town will be in 2030? This is a question in which we are effectively given a t-value. This gives us the t-value, and we are asked to find a p-value, right? So this is one of those kinds of questions. Given one variable, find the corresponding value of the other variable. Notice that 2030 is t equals 26, right? That's 26 years after 2004. And so this question boils down to, when t is 26, what is p? Well, you have this equation relating p and t. So if you know the value of one, plug in and figure out the other. So I plug in t equals 26, and I get, let's change our notation a little bit here. We get this, which comes out to 16,080. So that's our answer to the question. We predict the town will be a little more than 16,000 people in 2030. This is the other direction, right? When will the population of the town hit 25,000? This gives us a p-value, right? 25,000 is a p-value, and it asks us for a t-value. It asks us for a when question. So in terms of the variables, I could rephrase this as, when p is 25,000, what's the corresponding value of t? Well, again, I just use this equation right here. I set the p-value equal to 25,000, right? So that means that gives me this equation, right? When I replace p with 25,000, and I just do some algebra to solve the equation, right? So I think I'll subtract 6,200 from both sides and then divide, and yes, indeed. So here's what happens when you subtract 6,200 from both sides and then divide both sides by 380, and you come out with 49.5. Now, take a little care to answer the question. If you asked me, going back to the previous question, what will the population of the town be in 2030? And you answer 16,080, that answer makes sense to me. If I ask you when the population will hit 25,000 and you say 49.5, I don't immediately understand what you're talking about, right? Because t is the number of years after 2004. So a better answer to the question would be to figure out what year this puts us in. And 49.5 years after 2004 puts us in 2053. Okay, so that's a couple of examples. There's not really any new mathematics in this section. It's just applying our knowledge of linear functions to these scenarios in which two variables have a linear relationship. So sort of taking the scenario, building the relationship, and then answering some questions about the scenario using the model that you have built. Of course, there are a number of exercises in the notes and exercises. I've done a few here, 213, 214, and 215. So check those out. There they are. Give those a try yourself. When I post the notes, I'll open these up so you can see the solutions. And of course, there are exercises in the text as well. Take good care of yourselves, folks.